Hi Chem 100 students, it's Dr. Ricardo. We are going to be doing the third video in Chapter 10. Chapter 10 is on bonding, and the specific topic that we're going to talk about is called VESPA theory, or the VESPA model of molecular shape. So VESPA stands for valence shell electron pair repulsion model. So it's a lot to swallow, but we'll go through it slowly and it'll make a lot of sense. It's really very practical. So what is it for? It predicts the shapes of molecules and ions in which the valence shell electron pairs are arranged about each atom so that the electron pairs are kept as far away from one another as possible. And the reason for that is we want to minimize electron pair repulsion. Okay, so there's going to be three general rules that we're going to follow. So here they are, and then we'll take a look at some examples, and then we'll get into the specific electron pair arrangements that nature takes. So nature wants to take electron pairs that are repelled from one another on the same atom and place them around the atom in the most favorable geometry. So the most favorable geometry in 3 dimensions is how can you get these electron pairs away from one another if they repel each other? And the important thing that you have to realize is when you're talking about electron density is that lone pairs and bonding pairs are going to count equally. When we want things to get away from each other, I might have one bonding pair and one lone pair, and I would just count that as 2 groups of electron density. So 2 things. What arrangement would they take to get as far away from one another as possible? So we'll talk about all those different electron pair arrangements. So that's on the next page. But the general principle, how we're going to go about doing this, our approach is right here. So the first thing is lone pairs as well as bonding groups. Now, a bonding group can either be a single bond, a double bond, or a triple bond. So a single bond counts for a bonding group. A double bond is a group of electron density, 1 group, not 2. And a triple bond is a group of electron density. So why does a triple bond count just for 1 group? Because those 3 bonds are centralized between the same 2 atoms. So if I have an atom over here and an atom over here, I'm going to occupy the region of space between those 2 atoms. So the single bond is not going to be repelled from the double bond between the same 2 atoms. The things that are going to be repelled from one another are electron density going in this direction and electron density going in a totally different direction. That's what's going to be repelled. So just to repeat that again, because it really is so important, what we have to do is count up groups of electron density. So there's just 4 different categories, okay? You can have a single bond, double bond, a triple bond, or a lone pair. If you have any of these things, 1 triple bond counts for 1 group of electron density. 1 double bond counts for 1 group of electron density. 1 single bond counts for 1 group of electron density. And 1 lone pair, the 2 dots, counts for 1 group of electron pair density. And what are they trying to do? They're trying to get as far away from one another as possible. Second thing, you count the multiple bonds as a single group. We just talked about that. Third thing, the direction in space of the bonding pairs gives you the molecular shape. Okay, so the last thing we're going to predict, after we predict how are the electron pairs arranged, which is we're going to call the the arrangement of electrons pair is the EPG, EPA, the arrangement of electron pairs. The last thing we're going to do is predict the molecular shape, which we're going to call the MS. So those 2 things we're going to try to predict for each molecule that we have a Lewis electron dot structure for. So here's the first example, carbon dioxide. So we already know in carbon dioxide, right, we've done the Lewis electron pair structure, so I won't do that again. We know that carbon dioxide, the carbon is in the middle. It's got a double bond to 1 oxygen, a double bond to another oxygen, and each oxygen has 2 lone pairs, and the carbon has no lone pairs. So that's the arrangement, okay? So this central atom, count up the total number of groups of atoms around the central atom. The central atom is key. What's going on here doesn't matter so much because nothing else is hanging off, right? You don't have another atom here, otherwise I would care about what that angle is. But around the central atom, I have 2 total groups of electron density, right? And we learned up here that a group of electron density, a double bond counts as a group. So there's 1 group, there's another group. So this double bond is trying to get as far away in space as it possibly can from this double bond. So what would you do? Well, if I wanted to get as far away as possible, so I have a strawberry here. If I want to get as far away as possible, and here's my double bond on this side. Okay, so that's 2 electrons, and then there's another 2 electrons, and they're heading off to an oxygen atom out here. Well, where's the other 2 electron pairs going to go? The double bond going to go as far away as possible, which would mean straight across on the other side. So I would put my double bond exactly on the other side to make a linear arrangement. There would be an oxygen over here and an oxygen over here. So straight across is linear. What's the bond angle? 180 degrees when I go straight across. Okay, so this would be totally flat. I could look at it like this. Sorry, it's not perfect, but that would be my arrangement. It is a linear arrangement. How do I get as far away as possible? I go on the opposite side. I think that makes sense. Okay, so the arrangement of the electron pairs around the carbon, the electron pair arrangement, the EPG, would be linear. The EPA would be linear. And also the molecular shape would also be linear because there's no lone pairs around the central atom. There's nothing to ignore. The shape is described by the position of the atoms around the central atom. So if I go back up my camera a little bit so you get a little bit better perspective, if I take 2 grapes and make those the oxygen, there's nothing to ignore around the central atom. So my grapes, okay, I don't want to get any grape juice on my thing, so my grapes will be the oxygen out this side, okay, and the other side will be another grape. There's my double bond to the other side. There's an atom on this side, and there's an atom on this side. There's nothing to ignore. I don't have just electron density popping out. So the shape of the molecule will be the same as the electron pair arrangement whenever there's no lone pairs around the central atom. These 2 things may be different, and they'll be different in other examples, but they will never be different when there's no lone pairs around the central atom. So how would I describe carbon dioxide to the world? I would describe carbon dioxide as having a electron pair arrangement of linear, straight line, a molecular shape of linear, and the last thing that people ask you, what's the bond angle? Well, the bond angle for a straight line is 180 degrees. Go straight around, and you know that from geometry. Okay, so that's the first example. Okay, so now let's take a look at all of the possibilities. So we just did the first possibility. Again, if I have, this is the different arrangements of the electron pairs in typical situations. So now what do I call typical situations? Typical situations where I don't break the octet rule, so that I have a maximum of 8 valence electrons around the central atom. And in the cases that we're going to do, we're going to always have 8 valence electrons around the central atom. Okay? I can only think of one exception that we ever ask you where there's 6, and it would still follow the rules that you would expect. So, first question, what happens if I have 2 total groups surrounding the central atom? Well, how would 2 things want to get as far away from one another as possible? We just talked about that. They would tend to make a straight line, linear. If I had 2 twins and they weren't getting along, they were fighting, what would I do? I would stand right between them to keep them apart from one another. If you want to break up the fight, you go in a straight line between 2 people, right? So that would be the optimum angle. So that the electron pair arrangement is going to be linear. We just talked about this. Now in my picture here, I have atom A, and I just have a lone pair here and another lone pair. Remember, lone pairs count as electron density. This lone pair hates this lone pair. They're not headed towards the same atom. They're headed in different directions. So if they repel one another, they want to get 180 degrees apart from one another. They want to get as far apart as possible. Okay, well, let's rearrange this and ask ourselves the question, what about if we have 3 total groups around the central atom? So my example here of 3 total groups, I did it just to keep it simple with 3 lone pairs. So I won't put any atoms on it, but let's say I put one in this direction, okay? So go straight out of the top of the strawberry. Well, Three things, how would they best get away from one another? You don't yet have to take advantage of the third dimension. The second one would go down here at 120 degrees like a peace sign, right? And the third one would go over here. So that's kind of common sense too. If I had three things and they hated each other, they wanted to get as far away from possible, maybe this one has to come down a little bit. Does that look natural? Three things make a triangle. Perfect, right? This one hates this one, so it's going to make 120 degrees away from each other, 120 degrees away from each other, 120 degrees away from each other. No need yet with three things to take advantage of the space up here and the space below. When you have three things, you can maximize the separation with an angle of 120 degrees. You do not have to use this third space. In fact, you only make it worse if I start to pull this guy around here. Okay, so that looks very common sense to you. It looks very flat. If I look on it on edge, turn it over, it looks the same. So the bond angle, whenever three things are around the central atom, is 120 degrees. And what shape do we call that? Trigonal planar. Trigonal means three, planar means flat. Look at that, completely flat, right? Those things are flat. There's nothing over here and nothing over here. It's a flat triangle, trigonal planar. Now remember, this picture shows them as three lone pairs, but this could be a single bond, and a lone pair. This could be a double bond, a single bond, and another single bond. It's when you just count up the total number of groups around the central atom. If the total number of groups are three, the electron pair arrangement is trigonal planar. Okay, what happens when there's four total groups around the central atom? Well, that's a neat shape in chemistry. It's the first time since it's four, we're going to take advantage of the third dimension. So let me move my camera out a little bit and show you what the strawberry would do. So the strawberry would start off kind of like you think, where one would be up and one would be kicking out this way. Now, instead of going over here, you need to spread those bottom legs out a little bit so it almost looks like a camera tripod on the bottom with one guy sticking straight up. So this is the best way for four things that want to get away from each other to do so. The shape is called a tetrahedron. It tends to look like a little tripod with one sticking straight out of the top. It's hard for me to get the angles perfect. That's why I have some of the professionally made videos. Okay. So four things, right? Three go down and one goes up. Let me move this guy a little bit over here. So this is the natural shape of four things, okay? If I turn it over, it's supposed to still look the same. Now I still have three pointing down. These guys have to go a little bit down this way. You just have to readjust this. Not so easy to do. This guy goes this way. This guy goes this way. And then if I turn it the third way, it's still supposed to look the same in every direction. Okay? All right. So four things wrapped around one thing. What do we call that shape? Tetrahedron. Tetra for four. In this diagram, they're all lone pairs. It's a single bond coming straight out here, down the bottom. Okay. One coming straight up, one kicking down and back behind the paper. That's what those little squiggly lines look like. And this wedge is the one that's coming towards you. So think about a tripod on the bottom, three legs going down and one coming up. If you build that shape, the natural angle that things would want to get away from each other is a new number for you. This is a number from solid geometry, so you don't really see this much at school, right? It's 109 degrees. So don't try to take 360 and divide it by 4. That doesn't take advantage of the third dimension. You'd get 90, right? Making a straight a cross like this is not the best way to put four things around one, right? There's a straight, old-fashioned cross, right? One up, one down, one to the right, and one to the left. That's not the best way because the angle is only 90 degrees. You don't take advantage of the space on top or the bottom. So this is nature's way to wrap four things around one. Man's way is a cross. We're obsessed with 90 degrees, right? We build our houses all with 90-degree angles. 90 degrees is not the optimum way. The optimum way is 109 degrees. So whenever you have four things wrapped around one, they fall into this electron pair arrangement called tetrahedron. Okay, if we break the octet rule, okay, now there's going to be elements. Once you go beyond the second period, you can go above 8 electrons. So there are going to be species with 10 electrons around the central atom, 12 electrons, 14, even 16, okay? But it's not going to happen a lot for us. In case you see those, though, what is the natural shape? How does nature arrange itself? Now, this is a beautiful, beautiful shape. How does nature arrange itself when you have 5 groups around the central atom? Well, you make a triangle in the plane, just like you would ordinarily with a trigonal planar. So triangle in the plane is 120 degrees. I make my peace sign again. Now, this time I've got 2 more atoms to fit in there. Guess what? One goes straight up. Here's my triangle in the plane, right? Trying to make that straight, not so easy, okay? Triangle in the plane, one straight up, and one down on the bottom. Let me make this smaller so you can get a better picture of it. So here's my triangle in the plane. This guy needs to go a little bit more in the back, right? So there's my triangle in the plane. You guys see that? 1, 2, 3. What is the angle around that flat plane? 120 degrees. But I've got 1 atom sticking straight up, or 1 pair of electrons, and 1 on the other side. So I have a triangle in the plane, and 1 up, 1 down. So what are we going to call that? Trigonal bipyramidal. Why bipyramidal? Because you can actually connect these little lines, and you make a cool little pyramid on top that I'll draw for you in a second. So trigonal bipyramidal is a triangle in the plane, 1 up, 1 down. Okay, so you can connect this little triangle in the plane, and you can see your little triangle. So it's the only one that's going to have 2 bond angles. The bond angle in the plane is going to be 120 degrees. The bond angle between that flat plane and the bottom and the top is going to be 90 degrees. So let me show you what I mean when I draw it this way. Okay, let's see if I do this. Okay, so here's the central atom. Okay, here's one straight out. This guy is popping out of the blackboard, okay? Popping out of the paper. We have no blackboard. And this guy is back behind the paper, okay? And then here's the one that's straight up and the one that's straight down, okay? Now, you can visualize it a little bit better if I make, and just in pencil, connect the ones in the plane. So in 3D, try to picture this as a flat plane. Here's my triangle, and it has a top and a bottom. So there's atoms or lone pairs at the ends of each of these. There would be an atom here or a lone pair, atom here, 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 a lone pair. What's the bond angle inside the plane? Inside there, 120 degrees. That's what you know for a triangle. And between the flat plane and the one going up or the one coming down is going to be 90 degrees, right? I have a flat plane, I have a triangle, and then one straight up and one straight down, so this guy's 90 degrees. So 2 bond angles, okay? You're going to put other atoms up here or lone pairs of electrons, right? Here. And these are going to want to get as far away from those as possible. And how many total electrons in this situation? 10, 2, 4, 6, 8, 10. So this is an example of something that would be breaking the octet rule. Not going to be a big contributor for your test questions, but you may run into it once in a while. Okay, the last natural shape that we're going to talk about is what happens when you want to get 6 things wrapped around one. Well, this one is common sense, okay? What does nature do? Nature does exactly what man would do. You put 4 things in the plane, so you put 4 things in the back, in the front, on the left, and on the right. Okay, so that's 4 things in a plane. Then you put 1 on the top and 1 on the bottom. So these are all 90 degrees. Okay. Perfectly symmetrical, right? So I'm going to try to look at it. This is looking at it straight down. This is the top. There's the bottom. You can't see the bottom. And this is straight across. Here's 90 degrees. Here's 90 degrees. 90 degrees. 90 degrees. Flip it over. 90 degrees. And look, same thing. I always have a cross, left, right, top, bottom, outside, sticking out of the paper, in the paper. So 6 things wrapped around 1. Here's how it does it. It's called an octahedral. It's like, why octahedral? That sounds like 8 when there's 6 things. Well, there's 6 points, right? But there would be 8 faces if I draw this. So we'll go back to the trigonal planar one and I'll show you the faces. Now you don't see the faces, okay? So in this arrangement, what did I do? This guy is sticking out of the blackboard a little bit to the left. This guy's sticking out of the blackboard a little bit to the right. This guy's back behind, but a little bit to the right. This guy's back behind the paper a little bit to the left. So that's my flat arrangement. Here's 2 up and here's 2 down. Every one of these angles, even if you have the flat plane and the guy pointing straight up, every angle is 90 degrees in an octahedral. So let's go back to the trigonal planar and let me show you why you would call this trigonal bipyramidal. That's because yes, it has 5 points, 1, 2, 3, 4, 5, and the points are the places where the atoms were going to be. But if you connected the faces, look what cool shape this thing looks like. This looks like a little pyramid, right? There's a face here. There's a face here. There's one in the back. There would be one coming down this way. I feel like an art teacher, right? And there would be 3 faces on the top and 3 faces on the bottom. So that's why they call it trigonal bipyramidal. It would look like a little trigonal pyramid. Not a pyramid that goes around in a box, but a 3-sided pyramid. I don't think the Egyptians ever made pyramids like that, but they could have, right? A 3-sided pyramid instead of a 4-sided pyramid. So that guy's trigonal bipyramidal. Let me show you octahedral, the way 6 things wrap around 1 naturally. Right? All right, so let's make our central atom. Okay, so we're going to make our central atom. Then we're going to say, okay, let's have a wedge kind of popping out a little bit so I can sort of show it in 3D. Let's have another wedge popping out so I can show it in 3D. So what does that mean? Popping out towards you. Okay, this guy, when I do the spring, that's behind it. Okay, and then, so 4 things in a cross, right? 4 things in a cross. All the angles inside that cross are 90 degrees. That makes sense, right? And now, I've got one coming straight up and one going down into the blackboard. So the best way I can try to draw that is like that. So can you guys see, try to get that? All right, now, how many points are there? The points are the places where the atoms are going to be. Well, there are 6 of them. 1, 2, 3, 4, 5, 6 different places that can either hold a bond or a lone pair. If I try to make faces out of them, right, by attaching them like this, I get exactly a pyramid like you would think of in Egypt, right? A 4-sided pyramid on the top and a 4-sided pyramid on the bottom. So there are 8 faces on this shape, right? 4 up and 4 down. So those 8 faces are why it's called an octahedral, 8 for the faces. So in your head, just connect these lines over here, okay? I'm going to put an atom at each one of the corners or points. And if you made a face on it, that's where it gets the name of the shape. Okay? All right, so the next thing we're going to do is a really important reference table. Let me make it a little bit smaller. So what we're going to do is ask the question, what is the electron pair arrangement if I have 2 total groups around the central atom. Remember, it's all about the central atom because the central atom is going to define the shapes of the molecules. Right? If you're talking about the electron pair arrangement around an outside atom, if there's no other atom attached to it, like this grape over here, right? If this grape over here, what difference does it make if it doesn't have any other atoms attached to it, how its lone pairs are, because they're not connected to anything else? It certainly would matter if it made another bond to something else, then I would care about that angle. So I'm going to be concentrating on one atom at a time. And that atom we're going to talk about as the central atom, the one in the middle. Okay, so we'll go through these. So again, what do? For you guys, the total number of electron pairs, we're going to stick to just an octet for this discussion. So the total number of electron pairs are either going to be 2 total groups, 3 total groups, or 4 total groups. Now remember, what do we mean by a group? A group of electron density is either a single bond, a double bond, a triple bond, or a lone pair. Any one of those 4 things counts as one group of electron density. And groups of electron density try to get as far away from each other as possible. So 2, 3, and 4 are our main players for the total. Well, then we ask ourselves, how are they separated? Okay, how are they differentiated? Well, first thing is, what happens if both of them are bonding pairs? Then there's a trivial one. What happens if one of them is a bonding pair and the other one is a lone pair? And it turns out not to matter, because if you don't have at least 3 different atoms, there's no bond angle, right? There's nothing to ask a question about. There's no hinge. I need an atom here, an atom in the middle, and an atom on that side to ask myself, what is the angle between them? If I just have one atom here, and a lone pair, what difference does it make about this lone pair? There's only 2 atoms. So you got to get to more than 3 total atoms for it to matter. Okay, so first question. Total number of bonding pairs. So we have a central atom, and it's going to have 2 groups. How do 2 things want to get away from each other? Let's say they're both bonding pairs. So we have a double bond on this side, like in carbon dioxide, and a double bond on the other side. Well, we learned this already. How do 2 things want to get away from each other? This group hates this group, so they get away from each other by making a straight line. So let me put my atoms on the other side. So use grapes. There's my atoms on the other side. How do these things, sorry, it's not perfectly straight. How do these things want to get as far away from one another as possible? Make a straight line. Okay, so that's 2 total groups, right? And both of them are bonding. Group and group, right? Why are they both bonding? Because they have an atom on each side. If I go to look at the crystal structure of this, I'm going to see straight lines. My electron pair arrangement and my molecular shape are both going to be straight lines. Remember one of the things we learned before? If none of these are lone pairs, these 2 entries will always be the same. The electron pair arrangement will be the same as the molecular shape when I have no lone pairs. I have no lone pairs because I have an atom on the ends. Okay, what would happen if I had 2 total groups, but one of them was bonding and one of them was lone? Well, I pop one of the grapes off, right? Pull the grape off. Now, I just have 2 atoms, and 2 things define a straight line. So that's why I was saying it's a trivial answer. What difference, what angle this makes? There's no atom over there. The molecular shape is what are the atoms doing? So 2 things have to be linear because 2 things make a straight line. So if there was another entry here, 1, 1, it would still be linear, linear. Okay? All right, remember, this could be for carbon dioxide, where they were both double bonds on each side, or it could be for a molecule that had 2 single bonds and nothing else. Okay? Because double bonds count as, they don't count double. They count as a single group of electron density. So here's my carbon dioxide. It's still linear. This is a group, this is a group. I'd count them as 2 total groups. Both of them are bonding. So carbon dioxide is in this linear, linear. Okay, next one. Let me go just get some of my grape juice off of my hands so they don't get too sticky. What happens if I have 3 total groups and all 3 of them are bonding groups? Okay, well, how do 3 things naturally arrange themselves around 1? The electron pair arrangement is easy. It's trigonal planar. See, it doesn't matter how they break up. As long as there's 3 total groups, it's going to be trigonal planar for the electron pair arrangement. Notice that. Doesn't matter if they're all three bonding, two are bonding, and one is a lone pair, or one is bonding and two are lone pairs. The electron pair arrangement is how the electrons are arranged. That stays the same. Just like up here, two of them are bonding, or one of them was bonding and one of them is lone, there's always going to be linear. So here's my natural linear shape. So let's start off with the easiest one first. Let's have my triangle in a plane, right? That's trigonal planar. And let's put atoms on each of the three electron density areas. So if they're, I gotta get another grape. If I have three things wrapped around one and they're all bonding, there's nothing to ignore. I count everybody. So there they are, counting everybody, whoops. Right? So we know three things wrapped around one is called trigonal planar, right? That's pretty good. So there's nothing up here, it's flat, nothing on the bottom. So three things, all of them are bonding, trigonal planar. Is there anything that I ignore on here? No, because if I was going to take an X-ray crystal structure and outline the atoms, I would see a trigonal plane. I would see everything. There's nothing to leave out. So whenever this is zero, there's zero lone pairs, the electron pair arrangement and the molecular shape will be the same. See, trigonal planar, trigonal planar. There's nothing to ignore. Okay, what's the next one? Three total groups where two of them are bonding and one of them is a lone pair. Well, pop one of these grapes off. Oh, now I still have three total groups, right? So the electron pair arrangement is still trigonal planar. But what would I call this shape? Because I don't see an atom out here. Let me get a little smaller. Okay, I don't see, there's no atom here. So I'd have to skip this atom down at the bottom. And if I outline where the atoms are, I would see what looks like a boomerang. And that shape is called bent. Okay, so when there are three total groups, two of them are bonding and one of them is lone, the electron pair arrangement, how the electrons are arranged is still trigonal planar, but the molecular shape is bent. I ignore this side and I just outline the atoms. The molecular shape is an outline of the atoms. Okay, next one. Three total groups. Only one of them is bonding. The other two are lone pairs. So pop two grapes off. If I pop two grapes off, look at that. There's my three total groups. Oops, my other grape popped off on its own. Let me put him back on. Okay, there's my three total groups, right? So what is the electron pair arrangement? Still trigonal planar, three things wrapped around one. But only one of them is a bonding pair. And I don't care if this is a single bond, a double bond, or a triple bond. That electron density is heading between the same two atoms. How would you describe the shape of this? Well, there's only two atoms, so it's a straight line, it's linear. So let me show you that entry. Three total groups. One of them is bonding, two of them are lone pairs. The electron pair arrangement is still trigonal planar, but the molecular shape is linear. Look, looks like a straight line. I ignore this because there's no atom on the end. Good, looks like just like a straight line. Okay, next, let's get to the four total groups. Four total groups. What's nature's best way to wrap four things around one? Probably the most important shape to nature. Tetrahedral, right? That little pyramid, like a better way to say it, the tripod, right? Three guys kind of going down and one guy coming up. And when I turn it in any angle, it should look the same. I'm going to eat a grape. I got to get some new grapes. Okay, I need four grapes because I'm going to have, first, off the start, I'm going to have four things wrapped around one. All right. So I have four total groups. None of them are going to be bonding in the first example. Sorry, I lost my screen. Okay, four total groups. None of them are bonding. So put an atom on each side. So there's nothing to ignore. Whenever there are no lone pairs, the molecular shape will be identical to the There it is. Nothing to leave out. I still have my tripod. There's my tripod. Down, down, down. This is the straight up guy. That's better if I show you like that, right? I could swing it around. It's totally symmetrical, okay? Every way would be symmetrical. There's nothing to leave out. This guy needs to just get a little bit over here, okay? So that's the natural shape of four things wrapped around one. Okay, so that's nothing new. The total is 4. All of them are bonding. None of them are lone. The electron pair arrangement is tetrahedral. The molecular shape is tetrahedral, right? Whenever this is a 0, there's no lone pairs, this entry will be the same as this one. This entry will be the same as this one. Okay, pop one off. Let's pop the top guy off. Let me get a little further away. If I pop the top guy off, now it looks like a pyramid. You guys can't see it so well. Let me go down a little bit, okay? It looks like a pyramid where the top has been chopped off. Look at that angle, right? There's one guy in the back, one guy over here on the right, one guy on the left, but nothing on the top. So just the bottom guys are there, right? So if I was going to outline the atoms, I would just outline this shape here, and I have nothing at the top. But look, this is puckered up a little bit. This is not flat. So what are we going to call this triangular shape that's not flat? Well, we're going to call it trigonal pyramidal. Let me get that a little bit bigger. Okay. Trigonal pyramidal is going to be the tetrahedral with the top popped off. So it's going to look like 3 guys straight down and a lone pair at the top. Okay. So 3 total groups. One of them, 4 total groups. 3 of them are bonding. 1 of them is a lone pair. Electron pair arrangement, anytime there's 4 total groups, is tetrahedral. Notice that. But what do we call the molecular shape when only 3 out of 4 of the electron pairs are bonding? I should say electron groups are bonding. We're going to call that trigonal pyramidal. Let me try to draw that for you on some loose leaf real quick. Okay, so here's our central atom. Okay, so we're going to have the one guy out here. It's going to be to another atom. Okay, then we're going to have one guy kind of wedging out, jumping out of the paper to another atom. Then we're going to have the guy in the back to another atom, right? But the one on top is going to be to nothing, right? It's going to be just to a lone pair of electrons. And if we did the X-ray crystal structure, we only see the outline of the atoms. So what would this look like? It would look like that, where I ignore the top, right? Not a flat triangle, it's a triangle that's a little bit puckered, like that. Right? See how it's puckered, it's popping up? That's trigonal pyramidal. This is trigonal planar, a flat triangle. It's not puckered, see? There's space underneath, see the pucker? There's the pucker, okay? Look underneath. These 3 guys are kind of the top. This atom in the middle is popping up a little bit. Okay. So you'll see that better in some of the other professional videos. That's tetrahedral electron pair arrangement, and the molecular shape is trigonal planar. Okay, pop another guy off. Oh, what's the classic example of that? The classic example of that is ammonia. Here's the nitrogen. Here's the hydrogen coming straight down. Here's a hydrogen jumping out a little bit. Guy in the back. There's my 3 atoms. The last one is a lone pair up on top. I kind of don't see the lone pair. If I outline the atoms for you, what does it look like? Just looks like this part. It's like puckered, okay? So this is called trigonal planar. Very different. If there was no lone pair up there, if these 2 dots were not there, then all that nitrogen would do would be have a flat triangle. That would be trigonal planar. Doesn't have that. They do. This is kind of, the nitrogen is pulled up a little bit to be trigonal pyramidal. Good? Okay, so quick review. 4 total groups, 3 of them are bonding, 1 of them is a lone pair. Electron pair arrangement is tetrahedral. The molecular shape is trigonal pyramidal. Okay, next one. The great example of this is going to be water. Okay, I have my 4 total groups. 4 total groups make the electron pair arrangement tetrahedral. But if only 2 of them are attached to atoms and the other 2 are lone pairs, I have to forget about these 2. And what do I wind up if I just outline the shape of the molecules? Look, it looks like a little boomerang, just like we'd expect, right? So there's going to be, this guy is also going to be called bent. So 4 total groups, 2 of them are bonding, 2 of them are lone pairs. Electron pair arrangement is tetrahedral, but the molecular shape is bent. And the great example of that is water, and we'll do that in a second. So there's 2 bents. The first bent is bent up here when you have a flat triangle and you pull one out, right? That would be bent with 120 degrees bond angle. This one, when there's 4 total groups, 2 bonding and 2 lone pairs, the electron pair arrangement is tetrahedral and the molecular shape is bent. This would be bent with 109 degrees. So I'll show you the difference. So here's water. Water has 2 lone pairs on it, not just 1. Okay. Here's the oxygen. You can have a lone pair going straight up. You can have this would be one of the legs of the pyramid, of the triangle. Actually, you know what? Let me switch that. Let me do this. Here's my oxygen. Let me do a bonding pair straight up and a bonding pair. These 2 guys are flat, right? This is the wedge. This guy's jumping out of you, and this guy's a little bit back behind the blackboard. So there's the 2 lone pairs, right? There's the 2 bonding pairs. So if I outline the molecule, I skip the lone pairs, what does it look like to me? It looks like what we've been drawing all semester, right? Is that water has a molecular shape that's bent. The molecular shape is bent, whereas the electron pair arrangement, I count all the groups, 1, 2, 3, 4. 4 things wrapped around one is tetrahedral. And you can abbreviate tetrahedral TD. So that's the example of water. So when you see water like that, that's why I'm always drawing it. Those 2 lone pairs, count up the total group to give you the electron pair arrangement. 4 groups make it tetrahedral. How many of them are bonding and how many of them lone? 2 are lone, 2 are bonding. Therefore, the molecular shape is bent. That's this guy right here. Okay, last one is trivial. What does trivial mean? Easy. 4 total groups, but only one of them is bonding. Well, if only one of them is bonding, then it only has 2 atoms in it, right? So this is a lone pair, this is a lone pair, and this is a lone pair. So if I outline the shape of 2 atoms, it's got to be a straight line because there's only 2 things. There's nothing else to connect. There's nothing over here, here, or here. So whenever you're down to the fact that there's only 2 atoms, it's got to be linear. 2 things make a straight line. Doesn't matter what all those other things are, and I'm going to give you an example of that in a second. So 4 total groups, 1 of them is bonding, 3 of them is alone. Notice here, whenever you get down to just 1 bonding, it's linear. 1 bonding is linear. Okay, HCl would be a great example of this. Okay, electron pair arrangement around the chlorine is tetrahedral, but the molecular shape would just be linear. Okay, here's HCl, H to Cl. This is a lone pair, lone pair, lone pair. Okay, so if there's 4 total groups, somebody asks you, what's the electron pair arrangement? You say tetrahedral. They say, what's the molecular shape? Well, if you just drew what's the shape of the molecules caused by the way the electrons are arranged, you just outline the atoms, it's just a straight line. So the molecular shape is linear. Okay. If I tried to draw that here, let's do it this way. Here's our chlorine. Let's have this H being the guy that's straight out, right? So this guy's flat in the piece of loose leaf. Straight up will be a lone pair. The ones kicking out, wedging out, popping out of the loose leaf, there's a lone pair. And then back behind the paper and down is another lone pair. If I just outline the atoms, oops, sorry, the molecular shape is just a straight line because there's only 2 atoms. Okay, electron pair arrangement. How were the 4 electron pairs arranged? They're arranged in a tetrahedral. Good. Okay, let's do some examples now. So this is sort of your reference sheet, okay? If we were in a traditional class setting, if it wasn't coronavirus, you would have to memorize all this. But in the case of coronavirus, this should be a reference sheet. You should have it out to answer the questions. Okay, so let's take a look at these 4 examples. Okay, how would I go about doing hydrogen sulfide, H2S? Okay, so H2S or SH2, whichever way you want to say it. Let me get some fresh paper. Okay, let's start from the beginning. A couple breaks. Count up the total number of valence electrons. Okay, SH2 or H2S. What's the total number of valence electrons? Well, sulfur's contribution. Sulfur's right underneath oxygen on the periodic table. There's 1 sulfur. It brings in 6 valence electrons. Okay, the 2 hydrogens, each one comes in with 1. That adds another 2, so there's 8 in my picture. Okay, so I have 8 in the picture. Hydrogen can never be a central atom, so the S is going to be in the middle. You got to make at least a single bond to each of the 2 H's, otherwise they would not be in the same molecule. So there's my first 4 out of 8, plus I have 2 lone pairs. Okay, so we quickly draw it like this. This is the correct Lewis electron dot picture. Now let's answer the question. First question, what is the electron pair arrangement? Count up the total number of groups surrounding the central atom. 1, 2, 3, 4. Remember, bonds count as a single group, lone pairs count as a group. So I have 4 groups. 4 things wrapped around one is a tetrahedral. What's the bond angle inside of tetrahedrals? 109 degrees. And the third question, what's the molecular shape? Okay, the only thing, this is not very suggestive. This makes it look like it's linear. But in reality, we know the molecular shape that's associated, go back to the cheat sheet. If I have 4 total groups wrapped around the central atom, 2 of them are bonding and 2 of them are lone, that puts you right here, just like water. It's tetrahedral, but the molecular shape would be bent. Okay, so let me try to draw it in a more suggestive way. Instead of drawing it like that, draw it with the 1H kind of, remember, if I make a straight line, it's flat. So one guy straight up, one guy kicking out his leg here. This is all totally flat so far. This guy is not only down, but popping out of the blackboard. That's a lone pair. And the one that's not only down, but in the back of the paper, there's the other lone pair, right? That's my tetrahedron shape. So that's my electron pair arrangement if I count everything. But if I just outline the atoms, because that's all that I really would see is atoms, what does that look like to you? The molecular shape is bent. Okay, another example, CHCl3. Okay, first question, who's the central atom? I was nice in this one. I underlined it, okay? But even if I didn't, you could have predicted which of these 5 atoms had to be in the middle. Hydrogen is never in the middle, right? Because it's only trying to get to 2 total valence electrons. It's only going for a 2-tet. And chlorine is further to the right on the periodic table than hydrogen, so it's less likely to be in the middle. So it's the carbon in the middle. Carbon has 4 valence electrons. It wants to branch out more than any other atom on the periodic table. So let's write it up, CHCl3. Okay, let's count up the total valence electrons, right? So what's carbon's contribution? 1 times 4. What's hydrogen's contribution? 1 times 1. What's chlorine's contribution? Remember, chlorine is in the second to last group of the periodic table, right? Each chlorine would have 7 valence electrons, and there are 3 of them, right? Let me grab a periodic table for you real quick. Remember, these guys all have 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7. Look, right? 1 away from happiness, 1 away from having 8. These guys all have 7 valence electrons. So 7 times 3 is 21. So you have to add this. Oops, sorry, guys. This is 1 times 1 is not 4. 1 times 1 is 1. Okay, so you have 5 and 1 is 6, so you have 26 in the picture. All right, carbon's in the middle. Okay, put the 4 things around it. Okay, remember, when you're doing just the Lewis structure, you can go flat. In a minute, we'll get to the shape. They have to be attached to the carbon at least once, so everybody gets a single bond. Okay, how many have I used up so far? 2, 4, 6, 8. Now, start on the outside first. Put extra electrons in till everybody gets 8 around them and see where you wind up. Only contribute extra in when the central atom does not have an octet. So far, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I perfectly make it around with top, bottom, left, right, top, bottom, left, right, top, bottom, left, right. That's going to give you 8 around each chlorine, so they're all satisfied. This carbon is satisfied. It's got 2, 4, 6, 8 that it has. So it has an octet. And lastly, hydrogen is happy with 2. So every atom is happy in here. Okay, next question. What is the electron pair arrangement? Count up the total number of groups around the central atom. 1, 2, 3, 4 things wrapped around 1. What's nature's shape? Tetrahedral. What's the bond angle for all tetrahedrons? 109 degrees. You've got to memorize these 2 things go together. And lastly, what's the molecular shape? Well, there's nothing to ignore. If I built this model for you, this is what it would look like. I'll draw it on another page in a second. When there's nothing to ignore, you have no lone pairs, the molecular shape will be the same as the electron pair arrangement. So this will have a molecular shape also of tetrahedral. Let me draw that for you. Do that right here. Here's the carbon in the middle, right? What do? We got the guy going straight up. We got kicking out our leg to the right. This will be the hydrogen. This will be one of the chlorines. Okay, this guy is doing what? He's not only down, he's popping out of the paper a little bit. And the last chlorine, not only in the back, not only down, but going in the back of the paper. So that's my shape. Is there anything to ignore? No. I only ignore lone pairs. I don't have any lone pairs. This would look exactly like my tetrahedron, a pyramid with a guy sticking straight up like a tripod, like a camera tripod. So this would be tetrahedral, tetrahedral 109. Electron pair arrangement, molecular shape, bond angle. Okay, last one, PF3. Let me get you more paper. Phosphorus trifluoride. So first thing you always do, count up the valence electrons. How many in phosphorus? Phosphorus is right underneath nitrogen on the periodic table. There's 1 phosphorus, 1 times 5. It's in the 5th group over. 1, 2, 3, 4, 5. There's phosphorus right underneath nitrogen. 5th group over, skipping the transition elements. What's fluorine? There's 3 of them. Each one has 7 valence electrons. It's in the 7th group over when you leave out the transition elements, right? 1, 2, 3, 4, 5, 6, 7. Everybody here, we just did chlorine. Fluorine also has 7 valence electrons. So we got our 21. So guess what? I get my 26 again. Okay. So I have 26. Who's in the middle? The phosphorus, right? Why? Because phosphorus is further to the left on the periodic table than fluorine. Fluorine is less likely to branch. Why would you branch? You only need to bond once to get to 8. When you're at 5, you need 3 to get to 8, so you're going to make 3 bonds. So there's going to have my 3 fluorines around the outside. When you're just doing the Lewis structure, don't try to do shape yet. you just put them on a flat piece of paper. So we do top, bottom, left, right. Okay. All right. You have to be bound to the 3 fluorines. Otherwise, they wouldn't be in the same molecule. So put those 6 in right away. Now I have 20 more. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And guess what? I got 2 more to get to 26. That's when I go in with them. I go in with them when I still have some left over. So I'm not going to need to make multiple bonds in this one. I'm going to have a lone pair. Well, that lone pair is going to affect the shape, right? It's going to change the shape on it. So first question, how many total groups? 1, 2, 3, 4. If there's 4 groups around the central atom, what's the electron pair arrangement? Tetrahedral. What's the bond angle with all tetrahedrons? 109 degrees. What's the molecular shape? 4 total groups. 3 of them are bonding. 1 of them is a lone pair. Go back to your cheat sheet. 4 total groups. 3 of them are bonding. 1 of them is a lone pair. Electron pair arrangement is tetrahedral. Anytime there's 4 total groups, the electron pair arrangement is going to be tetrahedral. But what do we call the shape when I cut off the top, when there's only a lone pair at the top instead of a bonding pair? I'm going to call that trigonal pyramidal. Okay, so this is very much like ammonia. It's going to be trigonal pyramidal, and I'm going to draw that for you. Picture these 3 guys puckered down. Instead of being straight across like a T here, they're going down a little bit, and the lone pair is sitting straight up. So I can probably do it for you right here. Here's the phosphorus, right? First guy, straight down. Lone pair, straight up. Here's the dots. Here's this F. This F is popping out like a tripod. And the last F, down and behind the blackboard. So if I was to draw or outline where the atoms are, I skip. Let me put these extra lone pairs in here. They didn't matter because there's no atoms hanging off any of the fluorines, right? The bond angles are going to be determined by the hinge on the central atom. So outline the atoms, and I get a beautiful little puckered tripod, right? It looks like a tetrahedron with the top popped off. There's no atom here, so if I just looked at this, I would see the outline of the atoms, and I'd wonder, why is it puckered? Why is that thing sticking up? Because that's the effect of these lone pairs. It doesn't make a flat triangle. That extra lone pair is what makes it kind of pop up a little bit and have that shape called trigonal pyramidal. Okay, the bond angle is around 109 because all electron pair arrangements of tetrahedral are 109. Okay, so lone pairs require a little bit more space than bonding pairs. So sometimes what you see is in something like water, instead of it being exactly 109, the bond angle between the hydrogens turns out to be something like 107 because those lone pairs take up so much space. So let me see if I could show you that. Here's the water. Here's the 2 lone pairs. They kind of take up a lot of space. This one is in the front and down, and this is the one in the back. Well, these guys push out. They're very hoggy, and they squeeze these 2 closer. So instead of this being 109, you find in water, it's more like 107, but that's not a big deal. Okay? For us, we can just think about them as 109. I'm not worried about that. Okay, 1 hour, perfect. That's the end of this video. We're going to do one more video in chapter 10. Plus, there's a lot of fantastic professional videos where they have much better models than I have. I'm home stuck from coronavirus, so I'm only can use fruit and toothpicks. And but the good news is you get to eat the fruit at the end. All right, so have a great day, guys. Thanks for listening. Bye.